Hello, my name is Neil Hardy, and I'm a fifth year PhD student in the Electrical and Computer Engineering program at UCSC. I'm completing my thesis work in Dr. Ali Yannick's nanoengineering lab, and I'm focused on creating a new generation of optical brain-machine interfaces. Today's brain-machine interfaces are largely similar to that of the iconic Neuralink. Shank electrodes are inserted into a small region of the brain to record nearby cells. The big issues with this interface are longevity and throughput. The device causes inflammation and scar tissue that renders recordings unusable in less than 10 years, usually less than 5, and it only records from a tiny region of the brain. We at the Nanoengineering Lab have explored a non-invasive optical probe to overcome these limitations. This probe we call NeuroSwarm is essentially an entire system on a nanoparticle, as it wirelessly receives power, performs signal transduction, and broadcasts that data. These nanoparticles are injectable and magnetic, so they can be steered to regions of interest for both brain stimulation and monitoring. I'll now talk about how these two modes of operation work: monitoring with near-infrared light and stimulation with a technique called magnetothermal stimulation. For monitoring, near-infrared light is sent to the brain and scattered back to be read out. The nanoparticle is composed of 3 layers: a magnetic core, a metal shell, and what's called an electrochromic polymer coating. We performed simulations to find the best wavelength light to use to design the geometry of the nanoparticle, and found that there is a trade-off between penetration depth and scattering cross-section. So we use wavelengths between 800 and 1100 nanometers to balance good penetration depth and high scattering. We also ran simulations to evaluate the performance of the sensor. Electric fields of the neuron will enhance the scattering of the nanoparticles, and we found that NeuroSwarm with a magnetic core performs similarly to one with a purely dielectric core, which we previously reported, and it gives us a vastly enhanced signal, even when compared to other new neurophotonic probes such as quantum dots. For stimulating neurons, alternating magnetic fields can be sent through the brain to rapidly switch magnetic poles in the core of the particle, which induces heating. This triggers heat-sensitive ion channels in neurons and causes them to spike. Since only the core of NeuroSwarm is magnetic, we sought to answer if the thermal delivery would be hindered by the other 2 layers. We found that thermal delivery is nearly identical. Temperature profiles converge on the order of nanometers for particles of the same size magnetic core. Therefore, a particle of this design is viable for acting as a completely non-invasive brain-machine interface. And with that, I'd like to thank my advisor, my colleagues, and ARCS for funding this research. Thank you.